Okay, welcome everybody. So today, Michael Douglas will give us an introduction to language models, like how GPT works. And we are going to have dinner with Michael at 6:30. And if anyone who's interested, please send me an email so that I can make the reservation. So we're meeting here in the lobby at 6:30. If you're interested in dinner, anyone is welcome to come.
Okay, thanks everybody for coming. It's always a pleasure. Thanks for you. So, you've all read a lot in the newspapers and otherwise about the models. It's something which, I guess, is amazing progress in artificial intelligence. It's something where I think there is some prospect for physics to think usefully. They have actually contributed in a significant way already. And the thing I'll describe, that once it's heard of GPT and such things, is actually something you can easily define in equations and think about. I mean, nobody really understands it very well, so it's likely that we need new ideas from all sorts of fields to understand it. So the talk will be in 3 parts, and I want to make sure I do something in each of the 3 parts. So if I spend too long, more than 20 minutes in that part, signal me and I'll move on. So I want to kind of go through all the things that these models do. Again, people have probably read and played with it yourself, but I'll give a little bit of history and significant developments and ideas. And then the middle part of the talk will be really to write out these equations to define a transformer model and what is the thing doing. And then the last part will be people's ideas, discussion, speculation about how do these models do the things they do, because it's not obvious at all, because as many of you know, the defining property, the task which the models are designed and optimized to perform, is that you're given a string of words in usually natural language for the language models, and you're just supposed to predict what's the likely next word, some probability distribution over words that should in some sense match the distribution of natural language, say as sampled from the internet or whatever. And so on the one hand, it's a very natural and simple task, but it's very, very surprising, obviously, that it can solve, can do any of the things that it does, besides, beyond just making, convincing replicas of text. And so, why, how is it doing that? How can one fix the flaws? And obviously, yes, and so forth. Very, very big questions open on it. Okay, so I've written a number of references and somewhat small writing. So if you're interested, maybe you can take a picture of it, at the end of the talk. And I've written a sort of a timeline. So, these developments really happened very quickly, and so it's true. All the experts are not surprised that there are language models that can do reasonable facsimiles of text, but that they can do these extra things. It's really very surprising, and probably just because it's happened relatively quickly. So okay, so I'll spell out the problem in more formal detail in part 2. But the starting point is this idea of a statistical language model, which goes back a long time. In fact, there was important work at IBM in the early 90s by some of the people that went on to build or now running Renaissance Technologies. So that's a point of contact that some of you have with them. And it's a example in this, there's this kind of division of machine learning into supervised learning, unsupervised, or self-supervised learning, and reinforcement learning. That some of you will know this is very much unsupervised learning, in the sense that we're not giving it any signals or idea of what's right or wrong, other than, here is the corpus, the big body of text, and we're just trying to predict the next word in each case. And so it's predicting something, but it's not separating the data into input and output and so forth. And so there's this vast amount of data, was recognized. So 2012, kind of usually dated to be this modern period of deep learning. And not long after, realized that you're really, the amount of data you have is very, very important. It's better to formulate tasks that don't require labeled data, like say this is a cat or a dog or something. So more focus on unsupervised learning towards the later part of the decade. And then there are many ways you can make language models. I'll describe another one in part two for comparison, but the core idea behind this transformer model is what's called attention, and I'll describe that. And that was proposed in 2017 form that it's used now, and fairly quickly applied to language models. And probably the first one that convinced people that this was a valuable technology is called BERT. And both of these were by at the time to Google research, so deviling it out. And so BERT used this transformer in a more complicated way than what I'm going to describe. It had this kind of complicated business of encoders and decoders, which I won't go into. And so people simplified it in various ways. And then GPT-2, I'm not sure if it was the first, but it's the first well-known one that formulated the problem in this, what people call auto-regressive. So we have a sequence of words, we, 1, 2, okay, blank, okay. And so now we can formulate the problem statistically as a series of conditional probabilities, right? So fill in this blank. What is the probability of this blank following the word we? What is the probability? So we sample from this distribution. It might be that the most likely word is R, or it might be were. In any case, we have in principle defined this probability distribution in some way, and we sample from it, and then we use that choice to compute the next conditional probability. What's the probability distribution of words that could follow we are ... And so in principle, you could compute this in a variety of ways, but if you just follow this successive procedure, then the sequence of words is not strictly a Markov process, but it's conditional in this one direction. And so that's autoregressive. So GPT simplified the story to that point. And then this early GPT model had about 1 billion parameters, which again, if you know, these things seem very big at the time, but of course was not very big in light of what came later. And then by analogy to other things that people do. So what suppose you have this model that can then predict the next word. Well, now you want to apply it to some sort of task. It might be answering questions. It might be based on the data in some database. It might be something else. And the general way that people would do it, given this model, and I'll say a little bit more, but there's this training procedure where you have this huge corpus of text, some large fraction of what's on the internet, and you're basically optimizing a parameterized model, this transformer model I'll describe, to optimize some measure of how good this probability, so the model's producing a probability distribution, how well does that approximate the corpus, the empirical probability distribution. So you've done that, and then there was this idea of fine tuning, which said that now let's give it some data more associated to the task. Like if we want to do question answer, then we'll give it question answer pairs and so forth, and train it for a while on that. And people had some success with that. But what was not long, relatively soon discovered, and this was about 2020, is that these models, once they start to get about this size and maybe 10, variety of intermediate things here, they do what's called in-context learning. And what in-context learning basically means is that you've trained the model and on the huge data set, and then you just skip this step of now fine tuning and training it on the example, the big set of examples of the problem, and you either give it just one or two or three examples of the problem, maybe even no examples. You just you train the model. Now you just ask it the question. What is the capital of France? And that's it. And you just see if it works. And so around 2020, people started to see that, in fact, these models had quite a bit of ability to do this. That you could train the model just to predict the next word, and they could start to do all these closely related linguistic tasks, but certainly much more specific and requiring more specific capabilities, things that would start to look like reasoning. And so that got people even more interested in this direction. And then the performance had been improving as you make the model larger. So at this point, I'm just going to say more parameters. But how do you know that that's going to keep happening? And then an important development also about this time, late 2019, 2020, was this discovery or evidence that there are scaling laws in the performance of these models. So I'll talk about this in a little more detail, but you have some measure on the y-axis of how good or usually how bad. People usually talk about a loss function, from the kind of control theory literature to say that the bigger this number is, the more often the system loses. So, like getting the wrong or a bad estimate of this probability. And now on the x-axis, we could plot something with the number of parameters of the model. So I'll call that P. Or we could choose to plot number of size of the data set, so number of words that we train on. And I'll call that N. And either way, we get this nice power law relation. So if I say one, and over many decades, and thus you got this very nice power law, which had been observed before, in all various machine learning problems. The exponent, obviously depends on the problem. But again, this group, Jerry Kaplan and collaborators, including OpenAI, had the data about these big language models to show that this is also true for the big language model. And so that's now some motivation to keep increasing the number of parameters. If you had seen this, that would probably be motivation to not keep increasing the number of parameters. And on the other hand, the line kept going. And so one reason that was important is that this was not such a terribly expensive computation, but GPT-3 is a range of parameters, and the biggest GPT-3 was 175 billion parameters. And then the size of 10 to the 8, 10 to the 9, and then the size of the data set is of this kind of comparable or even hundreds of gigabytes, 10 to the 9, 10 to the 10. And then various, very, very much more loose intuitive arguments. I'm sorry, this is 10 to the 11 for 1.175 billion, and 10 to the 9 here. Much more kind of looser arguments suggest that these numbers should be roughly comparable. Okay, so 10 to the 10, so the textual data on the internet is somewhere at the hundreds of gigabytes range, and then you can also try to start training on like code and GitHub and stuff. So hundreds of gigabytes there. So that's a motivation to push it up to this hundreds of hundreds of billions of parameters, and then that's an expensive computation to train on that data set with that number of parameters costs hundreds of millions of dollars. Okay, and so you needed to have some reason why you think that it's worth doing. And anyways, they did it, and they they first did OpenAI and a couple of other, well, Google did this, and a couple of the other large companies did this. And now, of course, if all we got was this kind of a smooth improvement, then you might say, oh, that's nice. We need a bigger model. Now, there's this very kind of, I don't know, an analogy worth making between this and the history of particle physics, circa 1950, because people built accelerators. It's obvious that you wanted to accelerate particles to a higher and higher energies. There were cosmic ray experiments that suggested that you see something interesting if you could do that. And if you want to get it up to mega electron volts, you could build a little ring like this. But then the scaling means that inevitably to get to these higher energies, it's going to be more and more expensive. And so you need some sort of reason to believe that that's going to help. But the first thing you need is just some sort of a quantitative measure that says that, well, yes, there is a parameter which indicates the accelerator's energy. And it's very clear that we're making the machine bigger to increase the energy. And then we're probably in a new regime. And so one could make the analogy and say a similar thing here, that as we're probing new regimes by going down in this loss. I'll tell you what this number is, but it's basically the log of the the number of possible words at each point, roughly speaking. So the more possible words, the less you constrain the distribution. So it's an entropy, and the more you constrain the distribution. And so in this sense, there's an objective sense that you're making the model better. And so you might be probing a new regime. And then, of course, the interesting thing in particle physics is not so much that you push the energy up and you build some sort of curve behaving smoothly. It's that you cross thresholds and you make new particles. And you see all sorts of dramatically new phenomena. And so that's what kind of came out of doing this. Various these abilities that an ability to do some reasoning while you're answering questions, and now with the latest models, to write poetry and different languages and arbitrary themes and so forth emerge at some point here. And again, it's very mysterious, but at least one has some sort of quantitative basis for saying that making the model bigger will probe this new regime, and perhaps in a new regime, something will emerge. And then at this point, it's just empirical. It's essentially impossible to predict for something that we haven't seen, but we need to produce to see it. Okay, anyways, this type of general, very, very broad brush, scaling thing is certainly a physicsy thing to do, and was important in this motivation. And then as these larger models were studied, various, what kind of tasks would you do? I talked about question answering. Another one which more or less started to emerge in 2021 is this ability to generate code or to do programming. Where you can type in the description of a task in the natural language and ask it to produce a Python or some other program to do that. And again, as many of you probably played with or read in the paper, there was a version of GPT-3 called a Codex that was trained on GitHub basically after this initial language training, which I recall was released in early 2021, and showed enough ability to do that was kind of a product. And it's actually, the GPT-4 is enough better than the original Codex to they have not split the models into these different applications. But in any case, that ability is getting better. And the scaling continues. I am told, and so as many of you will have heard, the latest model, GPT-4, OpenAI did not publicly release all of the details. They have a paper which describes tests they've made. It does not quote this number of 1.4 trillion, which I've heard informally from other people. And so the scaling continues, but obviously cannot continue very much longer. If this costs 100, this costs several hundred million. It's not going to be presumably an SSC of language models, but you know, yeah, maybe this or GPT-5 will be the LHC of language models. But in any case, the other ideas, and I'll come back to this more with the part 3. So one which, again, you probably will have read something about is this idea of prompt engineering. Okay, so you can just typing in a question, say to get an answer to a question. You could give examples. You could say, here's a question of the type, like let's say math problems. What is 32 plus 76, or what is the airspeed velocity of the English swallow, and give it a few examples, and that will make it do better. There's more kind of silly sounding, but the real effects in this continuation process where you set it up to favor certain expectations. And so, for example, if you ask it a math question, true at this level, and you say, I am a mathematician who will try to answer your question to the best of my ability, you'll get answers. And if you tell it, I am a brilliant mathematician, fill in your favorite candidate there, you will get better answers. Okay, so the prompt influences the answers and the quality of the answers at that level. And again, you can kind of step back and say, well, the text that it's training on has words. Many of them are correct statements, many of them are not correct or misleading statements. So perhaps there's some conditioning in this general definition of conditional probability on our, the expectation that a word will reflect truth or some other desired property. Another and perhaps easier to explain version of this is what's called a chain of thought reasoning. So people tried, you give it math problems, high school, undergraduate math problems. There was a talk here, I think, last year, in the fall by Guy about the Google system, Minerva, which is an example of this, what I'm talking about, the math problems that it could solve. And if you just ask it to give the answer, which is perhaps implicit if you just state the problem, again, there's some level of performance. If in the prompt you say, well, you could give it the example of a worked problem with steps of the reasoning. First we develop this equation, and we solve this equation, and we use that equation. Or even just in the prompt say, in order to get the right answer, let's reason carefully step by step. Okay, and that's chain of thought prompting, and that measurably, that quite significantly improves the performance for these tasks that involve chains of reasoning. And that's an example of prompt engineering. There are some other techniques which are kind of secondary for purposes of this talk, but I'll mention them. So the GPT-3, as I said, kind of goes back to late 2020, but ChatGPT, which became such a sensation, is GPT 3.5, and the essential difference there was a technique called reinforcement learning by human feedback. And what this was to say was that they gave, you give it questions, it produces answers to the question, and then you got people just to rate, was this a useful answer to the question? And originally they would read this using a mechanical Turk, just having people out there that pay a little bit doing these ratings, and and then you use this as a secondary training signal. I'll describe the training, but again, you move, this was helpful. You change the weights of the model a little bit in the direction that enhanced that answer. If the answer is not helpful, you might change it in the opposite direction. And this had a very significant effect again on the usefulness as perceived by people of the answers. There's a related development of that, which is the main thing that Anthropic, company that started more recently, that in fact Jerry Kaplan moved to, is constitutional AI, where you start with that, and then you try to train a second language model, make those judgments to fit, in some sense, the human judgments of the quality of the answers, combined with statements, like, we would like the answers of the model to be helpful and honest and harmless and whatever other good qualities you would like. So this is an activity, and that again somehow really does affect the performance of these models. I'll come into again more specific and perhaps more scientific, but things that one can dig into more deeply, because this is a very empirical style of research. You work with this big model, and it's hard to guess what it's going to do. Okay, so the state of the art is what you see and play with. As you play with it, if you've done that, you know that some things it's amazingly good at, and many things it's kind of okay. And that includes a lot of the things that as scientists, physicists, mathematicians, and so forth, we would like it to do, a careful change of reasoning, or you ask it a question and we would like a correct answer with a correct reference backing it up. And these models are not that good at that yet. And I should say that GPT-4, which came out very recently, is quite a bit better at it, not ChatGPT. So play with ChatGPT, try to play with GPT-4. It's also capable if you get on a wait list, and that's the state of the art. And it's good enough in my experience that it's again comparable to going to Google search or Wikipedia to get the answer about a general, scientific question, something in our field. But if you then try to get it to, build up a chain of arguments to write a complicated program, it generally won't work. That's too much for it. And so, and then the extreme case of this is, something, just doing algebra, that we not every day, but simple reason about solutions of polynomials, and it does not do that reliably. I mean, that's the sort of thing where you could, clearly you would say the answer is to somehow combine this with mathematics, another tool to do algebra. So that's another idea people work on. But the basic thing that it's missing, if you have to summarize it, is that first of all, it has a accuracy, and people measure the accuracy for all sorts of tests by giving a benchmark. We give like 1,000 examples of the problem. It's standardized. 1,000 problems with their answers, and we just rate what's this accuracy in solving these problems. And even for the things that it's good at, these models tend to achieve up to like 90%. So something that's kind of at 20%, 50%, but 90%. And then that might be okay if for the 10% where it doesn't get the right answer, the model would realize, well, my argument is not very convincing. I'm not sure I believe this answer. I should go back and look for some other fact or do something else. But that's the thing which is missing. So it's not reliable in the sense that it can then step back and judge or even have any way of really working with effectively with the statement that, yes, this is a solid answer that you can build on. This one, maybe, it's not that the argument's not convincing. And so that's a big area of work to try to solve that type of problem. There are many ideas you can throw at it. And people have a lot of opinions. I'll maybe come back to that sort of the discussion. There are definitely people that think that if you can just keep scaling up, all problems will be solved, which is an extreme position, or at the very least, this problem might be solved. But that's not the majority point of view. The majority point of view is that there are things missing, and we can get back to that, perhaps in the discussion. So, okay, so let me, just to add another comment to that for people that are familiar with Kahneman and Tversky, this is, idea of behavioral economics and, the limits of rationality, that there's this idea that human thinking can be understood in terms of a system one and a system two. where the system one kind of takes the immediate judgment of the situation, that here comes a car, I better, move out of the way, or, you told me this, but that's crazy, I don't believe it. And system two, which is then more slow, the fast thinking and the slow thinking. So system two is the slow thinking, which is more reflective and can make a plan and, just find out and so forth. And so many people in this field have this analogy to say that these models are really doing a pretty good job on system one and a pretty lousy job on system two. So that's another way that people try to express the state of the art.
Mike, can I ask a quick question?
Please.
Just about your 90% number. Is that 90% even true for things like addition? I mean, really simple things, or are there things where it's extremely good?
Yes, I mean, again, if it's like a two-digit number, no, that's probably 100%. I mean, there are things where you can memorize all the answers.
Sure. But I mean, let's say 10, I mean, the 5-digit numbers.
Well, it's a time-dependent thing. I was about to say that there is up there, Lubeck et al. Is like the reference. There's another reference to the evaluates the mathematical abilities of GPT-4, but they already referred to Lubeck et al. GPT-4 might be able to do all the 5-digit cases, but I'm sure it can't do all the 10-digit cases.
Thank you.
Yeah. So okay. So in terms of references, so the current state of the art in terms of these benchmarks is this Lubeck et al. Paper, and then there's another different argument about what's missing from language models in terms of these kind of conceptual arguments, which is that there's this long tradition in cognitive science, understanding the mind in computational ways, that the human brain has various modules to do various, semi-instantial. I mean, you learn, but you have this built-in facility to help you learn. And language has long been postulated to be one of these modules. People like Chomsky, back in the 50s, and then certainly a lot of evidence for that. Right? It is the brain which is responsible for language. And then several other modules have been proposed over the years, such as something that specializes in what people call naive physics, which is just you see a ball, flying, you predict where it will land. Statements about if I put like this under gas, it will get stopped. But if I put like this through a paper bag, it will probably keep going through it. So it's all these things about naive physics. There's a theory of mind that allows you to make some sort of a model of what another person knows, doesn't know. There's causality, is another of these things. And then again, from this point of view, at best, the language models, the current language models have nailed this language model. You could really find enough kind of similarities to not literally say that there's a lower copy that's in the human brain, but that there's enough similarity that it's a reasonable scientific hypothesis to use one to study, to study their common aspects, but that these other modules are just missing so far, they weren't put in. And that point is made very forcefully in the Mahalo et al. Reference. Okay, so that's, I think, what I'll say about the first part of the talk. If there aren't questions, I'll go on to the second part of the talk. And okay, so the goal is to describe models that you have these sequences of words, and you're trying to predict the next word. You're trying to sample from a probability distribution of the likely next words. And so that's going to be built on, I'm not going to describe everything about neural networks and the like, and it's going to be built on that. And so obviously the first step is going to be to take sequence of words, word one, W1, W2, W3, up to this WK. Now we're trying to write WK plus 1. And so each of these guys has to turn into a number. So there's what we'll call the embedding now. And that goes from this discrete set of words W into some object, some vector space of dimension D. And we're just going to assign a different point in that space to each word. And that's the first step. And there's quite a lot already that you can say about that first step. And the D here, depending on the system, it was like 1,000 and these things. It's like roughly 12,000, I think, already in GPT-3. And so, again,
It's not equal to the number of words.
no, it's not equal to the number of words. That's right. It has to be, so I mean, well, step 0 before this, I should say it, is that there's what's called a tokenization. Just to say that words are a little bit too big a unit. And I'll give the example of supersymmetrization. It's a word, but it's a word that this audience has probably all seen, but another audience no. But if they know what supersymmetry is, well, even if they don't, they can see that it's made up of supersymmetry, iteration. And so this would have a natural tokenization into these 3 parts. And then it's those 3 things that would be embedding. Okay, so when you've got people talking about, the window is 8,000 tokens, that's the stuff that they're referring to. And the next step is this embedding on the tokens. And I'll just tell you a natural way to get an embedding which is much older than this, which is we're given this big text corpus, and within the text corpus, there's what are usually called a co-occurrence statistic. So the cat, that. And so we're going to basically pick a window length here. So we might say that it's 2 words in either side of the word. And so there's a window of length 5 centered in this case on the word sat. And then we're going to have the matrix where the rows are going to be the words that we're doing embeddings for. And now the columns will just be the existence or the number of so everybody's also be zeros. And because cat co-occurs with sat within this window, we'll give it a 1. And then this would be a way of getting indeed natural, not mathematically, photonic vectors, but given a big data set of text, we would naturally get vectors whose length was exactly the number of words or tokens. And is this definition clear? Yeah. And okay, but then what you can do to get a lower dimensional thing, and this is very standard thing that you can do with PCA. And but for people that call something to mind, basically what's called this matrix Z, then we're going to look at the symmetric matrix Z transpose, and then we're going to do the eigenvalue decomposition of that, and then we're going to keep the top D eigenvectors for some choice of D, and then project on that space. That can get us down to any D, and the statistical terms, the largest variation in this data set is associated with the largest eigenvalue of the subcovariance matrix and so forth. So that would be a really much used way of deriving embedding vectors. And it's reflecting this principle that linguistics said that you should know a word by the company it keeps. That if the word king often goes with ruler, maybe queen, maybe a country and so forth. And this says quite a bit about the meaning of the word king. And then a talk on this subject from 8 years ago would have pointed out empirically in the arguments that you can take embedding vectors derived this way, and you can find equations like V of king minus V of man plus V of woman. And so you just take these 3 vectors and you make that combination. So we'll call the embedding that. Then call it of king. Okay, and now there's an obvious intuitive guess for what word this is supposed to reflect. And now you could ask, out of this discrete set of word embeddings, what is this guy closest to? And indeed, it turns out to be kind of quaint. I guess already at this level, you are, it's been shown that you're capturing semantics of language, but it's obviously very limited because it knows next to nothing about the order of the words in the sentence and the grammar and all the rest. And so one way of proceeding from here is to say, well, what we really want is like contextualized embedding, which is maybe this is like the 0th order term. Then we want to add more terms to that have to do with the position of the word in the sentence and the other words near it and that kind of thing. So that might be one way of thinking about the problem. Another way, which I'm going to make for contrast, because I'm going to refer to it later, but I don't want to spend a lot of time on, is what's called the recurrent neural network. And this is the network, or the neural network version of the finite state machine. So at this point, I'm going to start using feed-forward networks. So we have, and so R1 goes to R2. So this is this big parameterized class of functions parameterized by something called weights, which are usually called W. I'm going to call theta. People often use to describe all these parameters. And then the canonical feed-forward network, just to helpful to remind you, is that you take the input, so it's VB input vector, you apply some matrix which unspecified, you know the domain, but now the range you choose some other R, on, and then you apply a nonlinear function to that, and you have another freely chosen matrix, and then nonlinear function of that, and then you can do that, iterate that combination as many times as you like. If we just say a 3-layer network, we might stop with a M3. And so now the parameters are the matrix elements of these 3 matrices. And then this can be a very general nonlinear function. It could be like tanh on each element of the vector is usually what's called relative, which is x if x is positive, 0 if x is negative. And so there's already quite a bit of theory about to what extent, in what sense these things are universal function approximators. I guess that's going to be like the basic ingredient here. It's possible actually count that, but I'm not going to go there. And so that's like the ingredient. And so now a natural way that you might try to do the operate on words. And so basically, let me complete the story here by saying, what do we do to represent this thing? So like if I were given these 3 words and we go over to predict this, then what we said was, well, we want the point which is nearest. Okay, I'll come back to that in a moment. And a more systematic way to do that would be to say, let's take the inner product of this vector. So like the list of all possible embeddings of words against WI. Look at the whole set of inner products with that vector. And of course, the closest one will get one with the largest inner product. So that might be the answer. We just say, let's take the largest inner product. But a slightly more general thing, because we know we're supposed to generate probability distribution, would be to use this to generate a Boltzmann distribution. So the word WI is going to be proportional to X beta times that inner product. And then of course the proportion means we normalize by the sum of all of those so that we get a probability distribution. And so then this is an inverse temperature. And this is what they do. So if you play with, there's the non-chat interface, for example, the GPT, where you can specify the temperature when you're sampling. And it's the inverse of that. Okay, so anyways, that's how you, so what I've reduced the problem is take these embeddings, we want to map from this list of vectors into another vector, and then this is going to be the final step to predict the probability distribution of the word. And now, what would, a very naive one would just be to take, some sequence of these words, and let's take, 5 words, and let's concatenate all those vectors, feed it into a neural network, R to the 5D, maps to R to the D, and that's our prediction. And then, that has some advantages, it's very natural, but obviously 5 words is not very much context. You might have to go way much farther back, using the sentence. And, it's, so that's the thing you could do. Okay, then what's the recurrent neural network? Without belaboring the point, we're going to have a feed forward network. We're going to feed in these successive embedding vectors I, W, okay, and we're going to get the output of the feed forward network. So this is out. But then we're going to also take another piece of output separately trained and feed it back in with the input. Okay, so the word K+1 will see the concatenation of the embedding of word +1 with this feedback, this state that came from, really depending on all the previous words. Okay, so that now is given a mechanism to, in principle, let the choice of this word depend on anything that happened in the past. And then this is already a universal computer. If you make these things big enough, you could model anything at all doing that. But of course, does it work practically? Okay, well, the other point I can make in terms of this very simple model is how do we choose these parameters? And this is this process of training. And the essential idea here is that we're going to try to fit a given empirical probability distribution, which just means we have this whole big corpus of text that we've somehow downloaded from the internet. We take each word, we look at this window of words before it. We're going to make the prediction for the probability of the following word, and then we're going to try to make that as close as we can to the empirical distribution, which is, within a certain set of words. Maybe that appears multiple times in the document. It's just counting however many times that word appeared. That would be the empirical distribution. And then we're going to just numerically try to optimize the parameters to maximize some measure of how good that match is. And the usual match for a problem like this to match two probability distributions would be the cost and entropy, effectively for an optimization as the Quebec-Lever convergence. And in this case of matching a general probability distribution P that we're predicting with a distribution which is every time we see one of these things, of course, although there was a probability distribution, we see a particular word. So we could say that's a term which contributed 1 to the probability distribution. You can effectively evaluate its cross entropy as just a sum over all of the words minus log the model distribution that we're trying to fit. So I guess if I want a loss function that I'm trying to minimize, then I'll probably do.
This is a definite correct answer. Whereas when people use ChatGPT, there isn't exactly a definite.
Well, that's a element of the probability distribution. That's right. So the model of predicting a probability, there is a definite embedding vector coming out, and then the way it gets used is we're going to compute its inner product with all the others, and then we're going to sample from that Boltzmann distribution. So if you turn the temperature down to 0, there is a definite thing actually. So anyways, it's that problem. So that we can compute that probability distribution, and that's effectively what we're feeding it here, but we're only evaluating it on the actual word that appeared in a given case. So basically, we summed over all the words in the document, and we're looking at the prediction problem for each word, and then the cross entropy really only depends on the probability that predicted that word would appear. Is that formula clear? So, and then you will substitute, this thing, and then whatever map is giving, these output embeddings, you to do that back substitution to figure out what this function is, and then basically what you're doing is creating this. Every time you see a word, you calculate this and you calculate its derivative, and you say theta for any given parameter here. So matrix in a neural network, matrix in this neural network, theta at the next step. Theta at the next step, some learning rate parameter, by theta, so the gradient. In this case, I could say, and of course, that's a Euclidean metric there. And in practice, of course, there's all sorts of techniques for speeding this up and estimating the metric that allow there and all sorts of stuff like that. But the problem is qualitatively determined by this loss function and through it by the corpus of text that we're trying to predict the probability distribution of. So in principle, I told you everything you would need to program this model. And again, you would find it's kind of okay. That's what people did, quite a bit of up until 2018, 2019. Okay, so now what's the transformer model?
Yeah, so it looks like your cross entropy depends on the shape of the embedding map. So
That's right. That's right. So in practice, you would not fix the embedding map.
So that's also trainable.
You would also.
But that's also correct. Okay, got it. Yeah.
So you might use this to start out.
You're optimizing both the net.
That's right. In practice, you would optimize both the network and the.
That's
very good. Yes.
Can I ask a question? This equation here between king and woman, is this something that you're hoping that the
I know the papers that show this, and you can give sort of derivation, but I can give references. That isn't all.
no, but is it something that the training will learn?
You don't even need all this. This would have been true just for these embeddings. Yeah. So, I mean, it will generally come out. That's right. I mean, in general, you can see a lot about the structure, but this was all on the level of embeddings of individual words. Now we're producing in terms of how can we make the embedding also reflect the context around the word. Okay, so the transformer model, now we've got these embeddings, this space RB2. We have a sequence of words of length L, usually called the window length. And in GPT-3, this is 8,192. And this is RD, which will be the factor here that we use to predict the next word. And this will also be a alternating sequence of two types of transformations, two layers. Okay, so we've gone from one to and one of the layers is just going to be feed-forward networks. So I'll tell you what the other one is. It's this potential of so this is a map from RD to the L. And it's going to be a sequence of vectors into tension applied to the sequence of vectors. And then let me look at the kth vector of the output. So this is the kth vector of the output. This is going to be the weighted sum over all the inputs. And in general, there might be some linear transformation, but I'm just going to do that times some weights. And what are the weights? The weights are basically going to be, okay, I'm going to give a name to this operation that mapped sequence of vectors into probabilities. That is generally called softmax. I'll write it out. But, where the people commonly use. Okay, so e to the some other beta product of and then all those guys to make these weights sum to one. And then this could be a more general inner product, or to be more kind of concrete. I could stick in a matrix B in that form. So what do? I to complete the kth output, I'm going to make a weighted sum of each of these vector inputs computed by using some sort of similarity between the kth input and all of the other inputs. So that's what this formula reflects. In other words, I feed in the kth input. This bilinear form is computing some sort of a generalized similarity. And this matrix can also be a matrix of tunable parameters. It might be projecting on some piece of the vector, it might be, some more complicated linear transformation. And then whatever we get there, we're going to look at its similarity to each of the inputs. And we're basically going to favor the input which is most similar to that particular input in this sense. And then the corresponding distribution of probabilities or weights will give us to weight all the inputs. So the rough summary would just be, we take a piece of this and we look at whichever vector down here has the most similar piece to what that is, and we take that one, but then that's a soft version of that. Is that clear? Yeah. Okay. So that's the attention there, and then the other type of layer is feedforward network, and that one doesn't mix the vectors. That's just exactly this guy applied separately to each vector with the same weights on each one, and then we iterate that guy some number of times. That combination is usually called a layer, and then this will be the depth of the network, and then we would take the last guy as the output for the purposes of predicting the following word. Okay, so that's the idea. Now there's a couple of further kind of changes to that. So one which is important in practice is that this thing is actually called the intention head. Because what you can do is you could imagine doing this operation several times with different matrices B here. This would be like attention sub 1, attention sub 2 with matrix B1, B2, and so forth. They might be comparing different pieces of the vector. You might be using different measures of similarity. But in any case, you can get out several outputs constructed with the same recipe, but different matrices B, and then concatenate those. And so that's this idea of attention head. And in GPT-3, there are I like that. Awesome. Okay, so in GPT-3, there are 96 of these layers. There are 96 heads. These matrices are actually 128 times D, so you project down to a lower dimensional space. I believe there's also a tunable projection matrix here, which projects you down to 128, and then you concatenate the 96 guys that came out that way. And the D here in GPT-3 to which check no, that's not 96 times 128. But in any case, those are the essential. Maybe it is. And you can tell me if that looks the same. So that's that. So then this is the entire recipe. There's one more. There's some other technical points that might be there. I haven't actually. It's been a while since I read the paper. But sometimes people take these intermediate vectors and like normalize them to normalized the based on the kind of the distribution of these things. Do some normalization. What's called Dash normalization and so forth. And you may be doing that. But that is kind of essential. That's more to kind of make the training work faster. Okay, but anyways, that's it. That's the whole recipe. So, if there are questions about it, okay.
Is it understood why this works so well with this?
No, it's one of every part 3. Yeah, so that's a training on this big, big chunk of the internet. And then these are kind of tweaks, you adjust the parameters a little bit more to make the answers more useful on that kind of thing. The hard of it is that. Okay. Okay, so now we can proceed on to part 3, and it's a very wide open field. People really do not feel they know very much about this. And again, there's already things you could say, even at this level. You could ask, well, is this some sort of a priori way of saying what dimension of embedding would be relevant here? And again, just in terms of this kind of model, you probably could say things. There's quite a bit that you can say about the problem of metric embedding. I suppose you had some sort of distances between pairs of words, a metric that you are trying to embed. There's many results about how big a dimension space you need to do that. The Johnson Limit test, for example, and then explicit constructions, would be some sort of a lower bound. I'll just mention that. Okay, another question which is potentially better understood, although not really well understood, is where do these scaling laws come from, which is not a specific claim to these transformers. It's really going to be a general thing about machine learning models of this sort, with they're trained that have some asymptotic regime of arbitrary, a very large number of parameters and a very large data set. And so let me not do it in any detail, but analysis. I'm going to do some earlier analysis, but I'll mention something about Alex Malone and Dan Roberts and James Sully. So I'm not sure I wrote that reference. So some of the references. Yeah. No. So let me write that one here. So, I didn't write it. I'm sorry. It's this reference, and then I'm going to mention this reference. Be sure. Okay. So there's a kind of a simplest model that if you thought about these things before, you would be tempted to apply. And these are earlier papers, which is that the scaling dimension is saying something about the data lying in a low dimensional subspace. So like it could be that although these are all vectors in 12,000 dimensions, maybe they focus and maybe they concentrate on a lower k dimensional manifold. Then that would be a lot of structure. But of course, it could be a nonlinear manifold, which takes a good deal of effort to learn. And then I think the basic, if you work this through, what is the actual number we're trying to have? Of order 10th or 15th, somewhere around there. And so then one predicts that the dimension you're going to get something like 4 over the dimension of the manifold. So one interpretation of the scaling law is that words and contextualized words and all this stuff tend to live on a 30 or 40 dimensional submanifold. But that's extremely naive. That's just one model. And I think there's no other empirical evidence for that. Okay, so another kind of model, and that's what Maloney and I'll do, is that you can make much weaker hypotheses. And in particular, you can make a hypothesis about the covariance matrix of the data. And so the covariance matrix made its appearance here. And again, the larger, this is basically the statistics version of multivariate variance. The larger eigenvalues are the dimensions which the data fluctuates a lot. The smaller ones are the ones where the data fluctuates a little. And in practice, though this is not terribly obvious, but in practice, the dimensions where the data fluctuates a lot tend to be the ones that don't have good prediction. And if you got too small, it's going to get swung by and so you should be able to say something based on the spectra of the covariance matrix. And so you can, compute it for this or for a transform model or anything, and you'll find that the spectrum of eigenvalues also has a power law. And so the, so we can introduce next slide. So here lambda is an eigenvalue of this covariance matrix, and the kth eigenvalue will be k minus alpha. Okay, so I'll define I'll use alpha someplace, but anyways, I'm not gonna make a long argument. This would define a power law exponent of the spectrum, and then actually it is related to the argument. We now will relate it to that alpha. So the way you make a analytic treatment of this is by now just granting that you're trying to fit random data, like Gaussian distributed data with this type of spectrum of the covariance. And then you can find that corresponds to the power law. And then, again, there's some evidence that this type of thing has been seen quite a lot over the years. It gets related to observations like physics law and so forth. And so that's a plausible answer, which is presumably taking it's using certainly less information than this very strong claim that the data constraints on a submanifold. And then this recent paper of Michelle et al. Will make contact with the other main branch of work in this direction I'm going to talk about, which is that this is the scaling is obviously very interesting. As I said, it's very motivating, but it's hardly telling you anything about why the model can like code or poetry or anything like that. And so how are we going to get at that? What I'm going to talk about for the last part of the talk is that basically the hypothesis that people work on lacking and the other is that you can write computer programs to do a lot of these tasks, maybe not to write poetry and Urdu, but to parse a statement in a language and to assign the words to various categories and to find common relations between them. So these were all the topics of the old style of artificial intelligence. Can you program a computer to translate language or do this or that? And the results from that, to again, really drastically oversimplify the big field of work is that you can program a computer to do all sorts of things. The problem is that the program has to come out in the real world like saying non-trivial things about language and common sense are extremely long programs. We have the time to write. Some vast number of facts that we all somehow learn when we're little. And if you have to hire programs to program them all in, that will take forever. Now you could hypothesize that this language model has learned a great deal of that through these statistics and text, but the form in which it's expressed that learning is like somehow this huge family of explicit models is encoding circuits which carry out algorithms like the ones that people had postulated in the earlier phase of the AI. And so that I sometimes refer to as a mechanistic or a circuit hypothesis. You can make it stronger. But that's I think the main thrust of the deeper work to try to figure out how these models work is to find evidence for arguments that these models are learning some sort of a circuit that you can, in principle, reverse engineer. And just to come back to this paper is trying to kind of bring that idea into this schema and show it out to say that the low eigenvalues down here are not just random, they're associated to these circuits. So how much more time should I take?
We're over time. So.
Yeah. Okay. Well, I don't have to give it, or I can, we can let people go, and then for people who are interested, I can talk about some of these circuit works, which is in kind of early days, but there have been some very interesting. So let me stop there.
I was wondering if you could talk a bit about positional encoding.
Oh, yeah, I really should have. And should have studied. I think there's a huge flaw in the thing I said here, but easily corrected flaw, which is that nothing here kept track of the order that the words were in. In fact, if you ask, is there some sort of a mathematical symmetry or other argument that would lead to this model? This is the natural equivariant model of the symmetric group. So exactly if you're looking for things that really don't care about the order of the words, then you might be motivated to write down this model, which is very good mathematically, but of course is very bad from the point of view of understanding sentences. And also, how do people do it? Well, that's trivial to deal with, because what you do is you take each of the vectors which was computed this way, and you concatenate to a vector which might just be the binary representation of the position of the word, 1, 2, dot, dot, dot. It's effectively what people do is now you've explicitly fed in that positional information as part of the embedding, and that's what people do. So I should have said that. Thank you.
I think the original paper uses like interleaving of sines and cosines.
Yeah, that's right.
Like page.
Well, there's this intuition that you want to get features on various scales, but it's this is a discrete. That's a continuous version of this. It's almost the same thing. I don't think it matters that much actually, but it's obviously better to do something systematic. But I don't think it matters that much what you do for positional encoding. Yeah, thank you. So that was the other questions.
Image models like DALI, are they also based on transformers?
No, they're not. That's based on, in fact, that's an even more physicsy thing. That's based on what's called a diffusion model. And the one sentence summary of that what is it? You can have like just the standard diffusive process where you have pixels and d by dt of the pixel is the second derivative on that array. So you have this diffusion that washes out the information. And now you try to run it backwards, and you favor running backwards in a way that reproduces some image in the data set. And so it sounds kind of crazy, but that's what they do. You train a model that does reverse diffusion, favoring producing images in the data set, and then you can run it on random data and something like an image in the data set. And then there's a way, I forget, of getting textual information in addition to that. So it's not this kind of model at all. But people have actually used transformers for transformers are good at almost everything. But people have done that. They're sometimes not better than the other things. Really better than the other things. Yeah.
It's really off the wall. Do you anticipate that progress will come from incremental improvements of these algorithms, or will it come from a totally different algorithm and this thing will just?
No, I kind of think that we're now in the right space, and it may not be that literally the transformer is the last word, but that the progress is going to come by adding things and modifying and making bigger systems that contain this transformer. Certainly, in the foreseeable future, that's what I would say. And so I hinted at some of that, like you might try to say, well, suppose you were trying to fix this problem that the system produces these wrong answers and doesn't seem to realize that it produced the wrong answer. Let's put in a second and somebody tries to look at the answer and judge, is this an answer that we should believe or not? And use that in some way. And that's definitely kind of control. Another piece that many people believe has to be put in is some sort of secondary database. And another weakness of these models is that this training procedure is very expensive, and you can't then just, like, if you want to give it some new facts, it's true, you can sort of fine tune one model, but that's complicated and expensive. You can't just, well, you can tell it something. You can just start your chat by saying, my dog is named Spot, let's talk about spot. And it will remember that, and it will remember that for, 8,192 characters. As long as the original sentence that she said about spot fits within those L tokens. And then as soon as it drops off the end, you will forget it. And so how do you fix that? Well, you might then attach this to some other kind of a retrieval. Might do something like this, to pick out data items that are close to an embedding and so forth. And that's another thing people work on a lot. So there is a variety of kind of standard ideas that show some promise, but weren't good enough. But so far as we know, for all I know, GPT-4 uses some of these ideas. They didn't make it public, but there's a list of ideas like that that people tend to think are valuable and will be part of the story. There's a very nice kind of a manifesto by John LeCount from about a year ago, where he spells out the things that he believes are missing. And he would put as number one on his list a planning ability. So these things, again, they have some ability, like you have to plan, your trip to Europe or something, and it will tell you something. And it often is something useful, so you better look, because you're quite likely that it will put you in paradise on a Wednesday, put you in your flight or Athens on Tuesday, because it doesn't have, again, the reliability to your plans. And so he would say, first of all, kind of a intuitive weakness of this regressive model is that it has no ability to postulate different possible plans, and then iterate and improve them and choose from them. Of course, you could do it by writing out long sentences of here was plan one, here was plan two, but then it all has to fit within this 8,000 word window. I should say that this algorithm, as I've described it here, if you think about the computational cost, it is quadratic in the length of this window, because every token, every word has to be interproductive with every other one. So it's because it's L squared. And so that's why the L is restricted. And a huge amount of work went into getting the L to be even that big. And GPT-4 does this deluxe version, which they don't give to everybody, which has a window size which is 4 times that big. Again, I think it's, because at FIRA it takes 16 times the cost. So that's why they don't give it to everybody. So indeed, if this number could be much bigger, and presumably it seems to be much smarter, but now this is a possible way to substitute for that. And then Jan LeCount will talk about ways to put in modules that are better adapted to a plan and to just have a whole list of possible plans. The thing he says, which is straightforward and touchful, is to do this idea of dynamic programming, basically, where you predict not just the next probability, but you predict the probability 10 tokens out, and then you will have some optimization over those 10 tokens, and then finally you get out the next token. That's a well-known technique, but again, kind of more expensive than what people are normally doing. But basically the answer, and this is well supported by everybody I've talked to, obviously everybody who I've talked to who works on this, but people who don't, who are not invested in the actual technology, they widely agree this is a breakthrough. It's not like it's the last word, but progress for foreseeable progress will incorporate those.
How do abstract scaling hypothesis guide the actual engineering of models, other than just simply increase the size?
Well, there's some more specific things about the scaling that I didn't describe. But when you're actually training the model, there are parameters, like for example, this beta, or this eta is a very good example. How do you choose that eta? And that's kind of an art. And then if you do these scalings more kind of carefully and so forth, you can figure out what should the eta be, so that you don't have to do trial and error, which if you're doing $100 million run, you don't. So that's one way that the scaling enters. But the big question of, again, like at 10 billion parameters, the thing was kind of, these logical word problems, and they got it down to 75, and now it has some sort of interesting ability to do it. Nobody has any clue how to predict those kinds of thresholds.
And in practice, how to test those hypotheses? the scaling law, the tail doesn't have to be like
You mean this one, or you mean the?
spectrum, yeah, or to test the inner spectrum and the.
Oh, yeah, that. Oh, I refer you to, I can recommend you to the paper, on the end. It's a very nice paper. They talk quite a lot about that.
Do we know whether the scaling laws change much if we use a different natural language? Chinese?
No, I don't think they change with the language, no. I'm not sure people have studied that in depth, but they might have. And that's already, the basic question would be to what extent is that number actually economically meaningful number that doesn't depend on other details. And I would say that's not 100% established. For these models, it does come out around 1/10, but in terms of error bars and do we really agree with the number, I don't think that's that well understood.
And what would happen if instead of a natural language we use mathematics?
Oh, yeah, okay. So if I had time for this, I would. So many of these papers are about analyzing the GPTs and the real language models, but a lot of these papers are about learning on toy problems, mathematical languages, things like that, where you have a much better idea of what are the circuits that it might be trying to implement and so forth. And so, yeah, so there is a big list of things that these are good at, subject to again this kind of caveat.
These machines have very short context window.
Yeah.
We can read the long book like.
We remember a lot. Although again, that's right. Well, again, I think our human intuition is compatible with this, but somehow putting facts into long-term memory, and that this is the retrieval disorder. You could attach a long-term memory. But that's right. That's a relatively short context. But again, people remember 7 plus or minus 2 ios. So from that point of view, this is not so bad. The short-term memory. Yeah.
That's related to Matthew's question. For example, consider multiplication.
Yeah.
Whether this machine, this model can learn the rule for multiplication after they see enough of it, or whether we need to add something.
It can. It's much harder than addition, but it can learn. The most interesting work of that sort was to learn linear regression. So people have tried as an interesting toy problem that you put in a sequence of, vector, number, like if x, linear regression, you're given a vector x, there's some y is some dual vector divided into x, and you're trying to estimate that dual vector of coefficients. And so now you can do that as a problem with in-context learning, which means that you don't give the model any of the data. You just take a model and the paper I was about to briefly summarize to draw it out. You do train it on the following task. You train it on the task of, let's give it 20 pairs of vector target, x, y, x, y, x, y. Now here's x21, predicts y, and it's supposed to learn the linear regression, at least squares, one of these linear regression algorithms. And it can do that, and it can do that quite well. And so it's learned a learning algorithm, because of course linear regression is what you would have called very simple, but a learning algorithm. And so that's potentially, that's more interesting than multiplication, at the very least, in the sense that it learned to learn something. And so I can recommend the papers that look at that. And an example that just to make, again, one of the points I was going to make from the circuit thing is that there's the problem of, let's postulate some sort of a circuit, some sort of computational thing that can do the calculation, but then could it actually learn that? That's not obvious. And so something that would clearly favor learning would be if the task was decomposable into steps. And if you can do step 1, you can solve 20% of the problem. Step 2 solves another 20% of the problem. So but that would really be a good thing. And so from the point of view of linear regression, you have a favor an algorithm that would use like a gradient descent. So you can actually have the thing inside its weights cook up a gradient descent problem, and then one of these layers can do a step of gradient descent. And an easy linear regression problem, maybe you can get a good answer in one step of linear of gradient descent. A harder one, maybe you need 2 steps and so forth. So that's an interesting paper to explore and getting that sort of point. So but multiplication is and arithmetic in general. The other the papers here, another toy problem that people, and one of the first that people were getting these kinds of interpretations for is modular addition, so ZP, addition and ZP. And then that it turns out there's an algorithm using discrete Fourier transform. This is now where you feed in a key component vector with a single one saying what's the corresponding to the number. And then an efficient algorithm, it turns out, is to do discrete Fourier transform, multiply the vectors, discrete transform back, and then there's this mandate algorithm who looks and, if you try and transform to do that, they're just they say they find reasonable evidence that that's being encouraged. This more recent paper with Andre Gromov, a physicist, and studied in quite a bit more detail. So multiplication is decimal multiplication. It can do. I know GPT-3 can do it up to like 4 or 5 digits, but there are problems that have no structure, and that's what people are more focusing on. The papers here, especially this recent one, talk about parsing and implement parsers and this and transformer circuits. That's I consider a significant step in this direction.
I have some weird questions. So if GPT can do some algebras and the linear regression, then can we use GPT to train the neural network just so that we don't use the
definitely. No, it's not weird at all. People definitely would like to, automate as much as they can.
Together, can speed up the solution
process. Exactly, that's right. No, very much so. We go make a startup with that idea. There are investors,
Investors.
You like this.
Questions?
What about images?
So it's definitely like GPT-4 has this ability, was also trained on images, although it's only in very limited release. Some people use the term foundation model to refer to the same strategy, but it's not just training our language, but multimodal. So yeah, and
I have more questions. Thank you.